Hello, Mr. Westwater here, and I'm going to go through a quick bit of teaching about hinges in mechanics. These are very similar to our ladder models, but with a couple of key differences which we'll talk about. So first, let's start by thinking about what we already know with ladders. Okay, we have here a ladder next to a vertical wall. There could be friction on the floor or at this point on the wall, which will act against the direction of movement. We'd end up with, it's not the best of normal reactions. There we go. Okay. So we have a normal reaction at the ground. We have a normal reaction at the wall. We would have some sort of mass working vertically down. Okay. And there may be other particles acting vertically down. Okay, we might have friction working against. These are the various forces which might appear. And generally, when we take moments around these points, we look at maybe places where there's a lot of unknowns, so the ground where we have the reaction and friction taking place, that might be a good place to do a moment. Alternatively, we might want to take a moment up here to eliminate our W. Various different strategies we can incorporate. Okay. Now, when we have a hinge, something like this, so I have my wall here, this represents the beam or the rod that we're doing, and this line is our chain or our string that is holding it in place. So if you will, this could start slanting upwards if we want, if this became a bit slack, but this is the model that we have set up. Okay, now if we think about what's going on in these models, we will have the mass of this coming down. So the tension in this rope at this point, there must be some sort of force holding it up. Okay, so we would have a tension force here, and this could be broken down into a vertical and a horizontal force. Okay, now these might not be perfectly matched. In fact, they won't be, because let's say, for example, I were to take moments around this point. Okay, we'd have a force going down, but there would be nothing holding it up. Okay, so this would just fall down. Now, with a hinge, this point is fixed. Okay, so this is our fixed hinge point. So if I have a force going down, thinking about taking moments from this point, then there must be a force going up to counteract the anti-clockwise movement going up there. Okay, so we definitely have a force going up at this hinge point. But we'd also have, if I think about forces going horizontally, I've got this horizontal part of tension going on, but there's nothing to counteract it. So there's also a force from the wall exerting outwards. Okay, and this is our general setup. Okay, so if I know, say, this angle theta, then I can work out this angle theta. They will be the same due to alternate angles, and I'd have t sine theta going up, t cos theta going horizontally. Okay, this isn't the only kind of model we might have. A slight adaptation of this, so actually what I'm going to do is, rather than redraw it, I'll just copy. Okay, and let's paste it just next to it. Okay, ooh, whoops. Okay, so let's say now we've got the same sort of setup, but this time our hinge is being connected at that midpoint, okay, yes, well then I've still got tension pulling up, and therefore we will have a breakdown into horizontal and vertical, and therefore I'll still have a force going out at the wall. But if I were now to take moments around this point, do we see that there are actually no our centre of gravity of, or our centre of mass, I should say, for the rod is just here. So there isn't actually any forces at the wall going vertically. Okay. Whereas my final example, if say our hinge was something like this, and the centre of mass was on the sort of to the right of this focal point, do we see it's trying to force it clockwise, if this is my focal point, and therefore the force at the wall would not be going up, it would actually be going down. Okay, so this fixed point at the wall will always have a horizontal force to counteract the horizontal force of the tension in the string, but it could have a vertical or a it could have a vertical force, but we don't necessarily know whether it's going up or down. We have to look at the other forces on that beam. Now, if it's just the centre of mass, then we can just use where the string or the rope is attached and use that as a focal point to work out whether it's going up or whether it's going down. But if there are other forces going on, like someone standing on it or an object being placed on the beam, then we might need to consider other moments as well. And so as long as we've got this force here, we can sort of label it in any direction, and if it comes out as negative, we can then know that it should actually be going in the other direction. But we'll see if anything comes to that as we go forward. Okay, so what I thought I'd do is I'd go through a past paper example, and hopefully we can see how this all works. Okay, so this is, I think, from January or June 2007. 2006, it's around that sort of time. We have a horizontal uniform rod AB, has mass M and length 4A. The end of A rests against a rough vertical wall, so this time it's resting, it's not fixed here, it's just resting against a rough rough vertical wall, which means we're going to actually have friction. So this vertical or horizontal force will be friction. Okay, so a particle of mass 2m is attached to the rod at the point C, where AC is 3A. One end of the light inextensible string BD is attached to the rod at B, and the other end is attached to the wall at the point D, where D is vertically above A. The rod is in equilibrium in a vertical plane perpendicular to the wall. The string is inclined at an angle of theta to the horizontal, where tan theta is 3/4, as shown in figure 2. Find the tension in the string. Okay, so first off, let's start labelling my diagram. So I've got tension going up, which means I've got a vertical component, I've got a horizontal component. This will also be theta due to alternate angles, and therefore this vertical force will be T sine theta, and this horizontal force will be T cos theta. Now I have force coming down at at C, okay, which is 2m. So this will be 2mg, and it's a uniform rod of mass m, so 2a into it will have a force of mg. Okay, so the way I like to think about this, as I said before, if I think about this as my pivot point, what are the forces at the wall going to be at A? Well, I'll definitely, as always, have a force exerting outwards. Okay, so we've got a force here. Let's just call this F. But we've also got friction acting on the wall. So if this is in equilibrium, then friction must be going upwards to counteract these two forces. So what I'm going to do, I'm just going to draw an arrow going up, and I'll label this FR. Okay? So, now that I've got all this set up, I've overworked for A, because all I'm trying to do is work out tension. And one way of going about this might be if I take moments at A, then I can think about T sine theta compared to our 2mg values. If I just compare horizontally, I don't really know what this force is, so I would have two unknowns. If I resolved vertically, I'd have two unknowns with T and F, and remember friction is going to be mu times F, but I don't know what mu is either. If I took moments around B, well, that would be no good because I'd eliminate T straight away. So by going around A, I have mg, 2mg, and T. Now you might say, well, what about sine theta and cos theta? Well, we're told about tan theta. Tan theta is 3/4, and I can draw a quick triangle out to help me with this. So if let's say this is theta, then opposite over adjacent, this will be 5. So sine theta is going to be 3/5, and cos theta will be 4/5. Okay, so I do actually have these values. In fact, we can write them in now. Cos theta is going to say this will be 4/5 T, and T sine theta will be 3/5 T. Okay, so find the tension in the string. I'm going to take moments around A. So I'd have 2A times mg, add 3A times 2mg, that takes care of these two forces, and then the only other force acting vertically is going to be 4A times that T sine theta, or 3/5 T. Okay, so let's work out what all of this will be. This will be 6A mg and 2A mg. Okay, and that will equal 12A over 5T. Now, and we could simplify this, I guess, into 8A mg equals 12 over 5AT. Now, A is in both sides, so we could divide through by A just to simplify this up a little bit, and then multiply by 5 and divide by 12. Let's just use my calculator to do that. I end up with T as 10 over 3. Okay, so that's A. Moving on to B. Oh, sorry, 10 over 3 mg. Yes. So, moving on to B. Show that the horizontal component of the force exerted by the wall on the rod has a magnitude of 8 over 3 mg. Okay. So, we're looking at this horizontal force. Now, as I said earlier, the only other horizontal force is this T cos theta, and we now know what T is. So, looking at B, I can resolve horizontally. So I'm just going to put this in brackets to indicate that I'm resolving horizontally. And I know that F, I called it, is going to equal that T cos theta, or 4/5 T. Okay, and I now know that T is 4 over 5 times 10 over 3 mg. So these will cancel, and be 4 times 2 over 1 over 3 mg. It's a show that question, so actually what I'm going to do, I'm not going to cancel because that might be perceived as being crossing out, and this comes out to be 8 over 3 mg, which is what we needed, and that gives me confidence in my first answer here for A as well. The coefficient of friction between the wall and the rod is mu, so we can write down, remember friction, I can now edit, we know what our force is, it's 8 over 3 mg, so this is going to be mu times 8 over 3 mg, going up. Given that the rod is in limiting equilibrium, find the value of mu. Okay, so now I can just look at all the forces that are acting vertically. Okay, so I know, let's start C, I know mu times 8 over 3 mg plus, what's the other force going vertically? It's just this T force, so 3/5 T. So plus 3/5 T. Oh, actually, I haven't labelled what I'm doing here, so before I get into this, I should let the examiner know that I'm looking at forces going vertically. And as it's in limiting equilibrium, you know, friction will be at its maximum, so we would use the value of mu perfectly. And our forces going down are going to be mg and 2 mg, so I'd write mg at 2 mg, which is 3 mg. Okay, let's simplify the left hand side as well, so I've got 8 over 3 mg mu. I'm just going to write it like that because mu is my unknown. Add 3/5 times T. Now remember, T was 10 over 3 mg. Okay, and here you can see this cancels quite nicely. The 3's cancel and the 10 and the 5 will cancel to give me just 2 mg equals 3 mg. So actually, we have mg in everything, so I could just say 8 over 3 mu plus 2 equals 3, or just 8 over 3 mu equals 1, and therefore mu comes out to be 3 over 8. Okay, so the process is very similar to when we have a ladder. We need to make sure we are taking moments around a certain point, and it will always depend on the question, but generally we actually always take moments around this pivot point because there's the most, there's the most unknowns going on here. We have a friction and we have a force coming out at the wall, but sometimes we might take moments around here. I definitely always think about moments from here to decide which way this vertical force is acting. Okay, so we're still always taking moments around one of those key points. We're resolving horizontally and we're resolving vertically. Now, depending on the question, you might do these in different orders, but you will always be required to do all three of these things when it comes to ladders or hinges. I hope you found that helpful, and I'll see you shortly.